Okay, our next module we're going to be looking at here is going to be module number 5, and you can see that it's going to be gear kinematics, analysis and selection. So all about gears. So let's kind of see what we have going on here. The first module is the learning plan. The first part of the module is the learning plan. You'll notice that we have 2 PowerPoints here. They're going to be referencing chapter 10 in our chapter or in our textbook. Okay, I have a part 1 and a part 2, so we'll work through those. We'll see how far we get. We may get done with all of it, but we can always split it up in the next week when we meet. We'll go over that. Even if we don't finish this tonight, we won't be continuing on Wednesday. Wednesday will still remain an open lab time. I will add the videos as we do those here that are going to reflect on each one of the lectures that correspond to the PowerPoints that we have above. And then we're going to have an assignment associated with this, which will be at the end of the chapter. So very typical of how we have been, you know, kind of going through each one of our modules. The next one here, this is kind of a fun little resource. This website has all sorts of different types of mechanisms and little drawings here, and they're kind of cute. So so I encourage you, if you wanted to kind of go through here, you can kind of hit this next button, and it shows all different types of mechanisms. Some of them are 4-bar mechanisms, as you can see here. These are different types of you know, indexing, in this case like a gear. So so I think it's kind of cool to maybe stimulate if you're looking for ideas or to brainstorm. There's like a ton of these out here. So one of the students in the other class had found this resource, and I thought it would just be kind of fun to have it out there. So that's all that's for. It's just for reference and entertainment, if you would. And you might find something that would be useful. Then you're going to notice that there's going to be the session recordings once we get them recorded out there, and then we have our assignment number 5. There are quite a few problems here, but none of these problems require any AutoCAD work. These are all going to be computations using the relationships and the equations that we discover in chapter 10. So so hopefully you're not too disappointed about that. I saw some, like, you know, sighs of relief. So so that's going to be that. It looks like a lot, and I'm not going to say that it's not work, but it's not as involved as what we've had in the previous modules. So let's take a peek at the first part of our learning plan here and open up the PowerPoint, which is in PDF format. And then if you're following along in the book, because we will be referencing sections in here, this is going to start on page 260, chapter 10 in our textbook. Okay. All right. So as we look at the beginning of the chapter here, the objectives that we have in chapter 10 are to really look at a couple different types of gears. There's, you know, we're going to be focusing on spur gears, which are the most popular, and we get a lot of mileage out of it because the relationships still hold true for the different types of gears. But there's going to be, you know, other types of more I don't want to say complex, but different types of arrangements that we'll be looking at that you would then go specific to that type of a gear for. But we're going to focus on spur gears. We're going to learn how to calculate center distances between gears based on standard equations, and then also calculate velocity ratios and train values. Okay, so between the two parts of our chapter here, we'll get through all that stuff. So first and foremost, the function of a gear is to transmit motion from one rotating shaft to another. Most often, we are looking at decreasing the speed, but we can use it to be what we call a speed increaser as well. So most often, it's going to be a speed decreaser. And we're also going to be changing the direction of motion. So if one shaft is going in a clockwise direction that has a gear on it that's engaged with another shaft with a gear on it, that other gear is then going to go in the opposite direction just by the nature of how they operate together. Additionally, we're either going to be increasing or decreasing torque, with decreasing torque being the most popular thing that we do with a gear drive. Now, we aren't going to be calculating torques or looking at forces, if you would. Our focus with kinematics is always going to be what is the motion that's occurring. So that's where we're going to be starting. In these problems that we're looking at with gears, we're looking at just the kinematics of it. And then when we get to machine design elements. Then we're going to be finishing up the designs with what is the material, what is hardness levels, rechecking to see what the stresses are. But that's when we're adding forces to the entire, design. Right now, we're not quite there. Okay. We're just looking at motion and then how much space are we taking up. Okay. Gears are mounted to electric motor drives to reduce speed and increase torque. So for instance, and I think it's probably coming actually in this example, in this chapter, but think about when you're at the grocery store and you're at the checkout line. The conveyor that is going to kind of take your groceries from one end to the other, down underneath, there's going to be a motor somewhere, and it's going to have a gear drive on it. And that motor is going at a pretty high speed, sometimes, 900, 1200, 1700 RPMs. But that's not very usable, especially for, a situation where we have a grocery conveyor. If that would be like direct drive to a motor, that would be spinning really fast, and you'd set your, lettuce on it and the lettuce would go flying, right? So, and then the other part of that is it's not going to have much torque. And even though we're not dealing with torque here, if we would try to, for instance, put a case of water on that high speed conveyor belt, we would probably stall it out because it wouldn't have much ability to do work. So, and that's just by the nature of it rotating so fast and not having a lot of torque associated with it. So in that case, we want to bring the speed down first and foremost to be usable. But then secondly, what's going to inherently happen is we're going to be able to increase the torque, which is going to allow us then to move things along that are going to be of more of a heavy nature, like a case or two of water, which wouldn't be uncommon. So let's first start with looking at different types of gears. So when we look on page 261, and this is going to be figure 10.3, we're going to see a number of different types of gears that are listed here. So on page 261, and when we look here at this column right here, we're going to be focusing on the different types of gears that we have here and kind of seeing them side by side on how they're different. So the first set that we have here is looking at what we call spur gears. A spur gear is going to be the most popular type of gear, most run-of-the-mill, if you would, entry-level gears, and they're kind of that classic look. They have what we call an involute tooth profile. And what happens is that they are going to engage with one another. So whenever oopsie, sorry, that focus went in the wrong direction. Whenever we have two gears that are in mesh, for instance, they need to have the same tooth size and profile. Okay. So for each one of these gears, we can say that they have the same size tooth. We'll talk about what that's called. It's called diametral pitch, and we'll be able to calculate that and determine that. You'll also notice we had talked earlier when we have the rotational direction on one gear, that means that the other gear is going in the opposite direction, just by the nature of how the teeth engage and how the motion is going to be relative to one another. So the first kind is going to be spur gears. The next kind is really still a spur gear involute tooth, but this is called a rack and pinion, where we're taking one gear that's going to be rotating, and we're going to then engage with basically a gear that's laid out flat. And then this is going to be translational motion or straight line motion. So, so this is going to rotate and this is going to go back and forth. The next kind that we have here is another spur gear application, but this time this is an internal type of a gear. So you'll see that the teeth on the inside then engage with a gear that's been rotating on that inside portion. Again, the teeth are going to have to be the same size and shape so that they can be engaged and then be able to move relative to one another smoothly. The next type of gear that we have here, gear set, is called a helical gear. Now you'll notice one distinct difference between the helical gear and the spur gear is that the spur gear has their teeth they're going to be in line with, if you would, what we call the face of the gear. Over here, they're at an angle to the face of the gear. And what that does for us is it actually increases the amount of force and torque that we can push through because of the teeth being at an angle, there is a longer line of engagement. So we can push more torque and force through those with the same physical size or the width of the actual gear. So helical gears can push more torque. The other thing that they do, actually two more things that they do, is because the teeth are at an angle, they can actually take what we call a side load. Okay, spur gears can't. All right, so if there's any side load, you know, on whatever we're engaging with or what's supported on the same shaft, we wouldn't be able to accommodate that with a spur gear. You have to go with a helical gear instead because it's got the capability to resist side loads. It also is going to be a quieter gear set because at any given time you have more than one tooth engaged because one is like leaving as the other one is starting. When we've got spur gears, you're clicking them together, and as one leaves, the next one is coming in, and they're a noisier gear set for that reason. So this one's going to be a little quieter, and it's also going to be able to push more torque through it. The next one that we have here is a herringbone. So as you look, it's easier probably to see in your book, but you'll notice that we have gear teeth that are going in two directions here. And this again is going to provide for us a more smooth, quiet application of the gears, but it also is going to be very low profile. Okay, so that you can have the same amount of force and torque going through as you would for a spur gear. The next one is about bevel gear. The bevel gear in this case, you're going to notice that we have a smaller, which would be what we're going to find out is called a pinion, and then the gear is going to be the larger of the two in the set. And they're two different sizes, but now our shafts are no longer what we say are parallel that we see in each one of these cases. Now we're at 90 degrees to one another. So you can change the orientation then of the rotating shafts. Miter gears are that very same concept of changing to a 90-degree orientation, but miter gears are going to be the very same size, okay? So a miter gear is only changing the direction 90 degrees, and now the gear teeth are 45 degrees across that face width, but you aren't changing the velocity ratio, as we call it, or the ratio between the two. They're going to be the very same number of teeth and size. And then the last kind that we have is going to be a worm gear. Okay, so a worm gear has a spiral, and that's called the worm, and it's going to engage with what's very similar to a miter gear, or I'm sorry, a helical gear, as we see here. And so that helical gear then has the ability to be a lot more, they call it zero backlash. So we're going to be looking at the spur gears in just a little bit, but backlash is going to be, if you would, the slot between the two gears, and it's how accurately those gears are created. And sometimes when you're changing direction from one way to the next, and back the opposite way, you're going to have a little bit of a gap in there, like an air gap from when you were going in one direction. There's going to be a gap, and then you're going to engage in the opposite direction, and that's called backlash. Worm gears have zero backlash just by their nature on how they're created. So, so they're nice that way. They're very accurate, very expensive, very expensive. Okay, so that's different types of gears. We're going to be focusing on spur gears. So as we turn the corner here and we turn the page, at the bottom of page 262, we're going to be looking at a number of these terms. So instead of and we're going to be looking at some tables and some figures as well in the next couple pages, but we'll start on page 262 at the bottom and really kind of look at the tooth profile of a spur gear. Okay. All right. So as we look here, we're looking at a couple of the teeth along the perimeter of a gear. Now we call this a spur gear because this is called an involute tooth profile. So as we look at that profile, that is very specific to the type of gear that we have. And as we kind of look at the side view here, you're going to notice that the teeth are all around the outside, and we have this lower portion, which is called, sometimes referred to as the root, but from what we call the pitch circle down to the bottom of that tooth, the root, that is called the dedendum. Okay, and you'll see that right here. So from this kind of center line circle right here down to the bottom of that tooth, that's going to be called the dedendum. The addendum is going to be then the top portion to the top of the tooth. Okay, now this circle right here that runs along, okay, that's called the pitch circle. Okay, the pitch circle is really important to gears. It's what we call the effective diameter. It's the point of engagement from where one gear is going to be pushing up against the tooth of the next gear. So if we skip ahead a little bit and we look at, trying to see, there's one particular, maybe it is this one. Let's turn the page here. On page 264, I've got a couple things coming in here. On page 264, we've got two teeth that are engaged with one another. Now, if this would continue, this is going to be the dedendum down here, and this is the next tooth coming in. This circle right here is that pitch circle, but it's the point of contact for those two teeth to be engaged with one another. It's also important because at that point, the addendum is actually shorter than the dedendum, and that's by design because we don't want it bottoming out or, catching the bottom of that tooth and interfering, okay? So the dedendum is always going to be greater than the addendum, and it's going to be off of that pitch circle, that effective diameter where the engagement of the teeth actually occur is what the pitch is going to be on. Now, the pitch diameter is along that pitch circle, okay? And when we calculate, for instance, center lines later on, we're going to be going off of the radius of the pitch circle of each one of our gears, and we'll be able to calculate that based on how many teeth are on a gear and what the size of the tooth is. So pitch diameter is what we call the effective diameter, that point of engagement that we're expecting on one gear to the next. Now, the width or the depth of an actual gear tooth is going to be what we call the face, okay? The longer the face, you're going to have line contact, and I'm going to kind of draw it along here to distribute what we would calculate to be the forces that are going to be pushed then through these gears. Now, in kinematics, we're not going to be calculating these forces, but you can imagine that we don't have point contact, we have line contact. So the wider that face width is, the better it is, the less stress that we're going to have on a gear tooth, okay? So face width becomes an important variable as we start looking at stresses on teeth. Okay, now if I want to calculate what that pitch diameter is, all right, I need to count the number of teeth and I need to find out how big or small that tooth is. So as we look up here to equation 10.1, oops, I'm sorry, 10.2, the capital P sub D is called diametral pitch, okay? Diametral pitch is equal to the number of teeth divided by the pitch diameter. Now, as we've been doing for kind of a lot of these units, we've been organizing our equations on equations sheets. There aren't a ton of gear equations, but there's going to be a couple that we're going to want to make sure that we know and have in mind. And this is going to be one that we're going to want to write down. So I'm just going to kind of start a gear equation sheet here. And this is going to be my first one that I'm going to list. So capital P sub D is equal to N divided by D. All right. Now, D right here, I'm going to put that one first. That is the pitch diameter. Okay, pitch diameter. And that's going to be in, and we're going to use English units, that's going to be in inches. Should use my normal brackets for units, right? So this again is going to be the effective diameter for which the teeth are going to engage with one another. Okay, pitch diameter. All right. Capital N is going to be the number of teeth. Okay, capital N is going to be the number of teeth. So we physically can count the teeth on a gear and use that in this equation. And then capital P sub D is diametral pitch. Okay, diametral pitch. Now the units for diametral pitch, I'm going to put them down below here, are going to be teeth per inch. Okay, teeth per inch. Now, diametral pitch, pitch diameter sound very, very similar, but they are very different things. So pitch diameter is always going to be the dimension of the diameter of the circle that is going to engage with the gear that's in mesh. I'm gonna look at another diagram, and this one I think shows it a little bit better. So on page 273, here are two gears that are engaged with one another, okay? And as we look at this illustration, you'll notice that they show some teeth that are gonna like be engaged or are engaged currently, but then they continue to represent this with a center line circle going around the outside for the larger gear, and then that same center line circle for the smaller gear. And if you look close here, that center line circle represents the pitch diameter, okay? It's that point where on the pinion, it's going to engage with the gear, okay? Pitch diameter is a physical distance in inches. So look at the small or lowercase d for each one of these is the pitch diameter, okay? Diametral pitch. Diametral pitch essentially is, let me zoom out, how large or small the tooth is, okay? So as we look up here, this says these are standard tooth sizes. These are called out in diametral pitch numbers. So for instance, if we have a number 3 tooth, it's a big chunky tooth compared to a 48 tooth, okay? These are all diametral pitch sizes, but these are standards. So notice that we don't have every number. So we go from 3, 4, 5, 6, then we skip 7, we have 8, we skip 9, and then we have 10, 12, and so on. So there's standard numbers or standard diametral pitches for different size teeth, okay? So the larger the tooth, the smaller the number. The smaller the tooth, the larger the numbers, okay? Now, if I know how many number 8 teeth are on a gear, if I know that's a diametral pitch of 8, and I know that there's 20 teeth, I can calculate the pitch diameter, okay? So when I'm laying something out, I'm interested in pitch diameter because I need to know how much space it's going to take up, okay? But when I'm specifying teeth, I have to make sure that I know it's diametral pitch, because if I'm calling out a number 6 tooth or number 6 diametral pitch, it has to then, both of the gears that are going to be engaged have to have that same diametral pitch, okay? So diametral pitches have to be the same between teeth that are going to engage. So if I have 2 teeth that are engaged, they're the same size tooth, the same diametral pitch. They can have different pitch diameter sizes because they're going to have different number of teeth on them, but their diametral pitch has to be the same. So as I look here, underneath, I'll try to make this kind of make sense. Hopefully it looks okay underneath. I don't know, it's going to be a little shiny, I think. But this is kind of a cool little a diagram here. So what we have is the red on the bottom here. It's going to be a certain size, and then the yellow is going to be another tooth that's in engagement. So these 2 teeth have to be the same size in order to allow these to move freely back and forth, okay? And what's cool about this is you're going to notice that there's I know it might not be easy to see on the overhead, but there's a yellow line here. That's the pitch circle. And if we line that up here, that's the point of engagement on the 2 teeth that come together. So the pitch circle is going to be here for the top one. The pitch circle is going to be here. That's the pitch diameter, okay? So a lot of times we hear it called the pitch circle, pitch diameter. And then their center of rotation is going to be at the center of the gear. And where they actually hit is going to be that actual point, that what we call effective diameter, okay? So that we always want to know for instance, when we lay things out, to know how much space this is going to take up, all right? But diametral pitch is the size of that tooth. So as that gets bigger and smaller, that's going to then change this diameter as well, depending on how many teeth are on there. Now, I also have a couple of gears here, and I'll send these around. Unfortunately, online, you won't be able to get the same experience, but when I look here, and I've got these two gears, zoom in here. You're going to notice, and I know it only can go by sight here, but these move very freely with one another because they have the same size tooth. They have the same diametral pitch, okay? Now, this looks pretty darn close, all right, this one here. But if I try to put that in engagement, you can feel right away it's not even, and you can see that they're not fitting together, okay? So what this tells me is that these do not have the same diametral pitch, so they would not be able to run freely together. But if I match it up with this one, all of a sudden now I can feel that difference, okay? So in class here, I'll pass these around for you guys to kind of just feel that difference, but this is all about the size and the shape of the tooth. Diametral pitch has to be the same, okay, for things to run correctly in engagement. So when we get to the point and we're specifying gears that are going to be for a gear drive, for instance, that's going to be critical that we make sure that the two teeth that are engaged are the exact same size, and that's going to be by the diametral pitch, okay? So if I go back here, pitch diameter is that small d, diametral pitch is going to be capital P. They sound very similar. Diametral pitch is going to be the size of the tooth. Pitch diameter is going to be the physical size. Okay, we talked about number of teeth. We talked about, oh no, we didn't talk about circular pitch yet. We'll look at that. Oh no, we did talk about circular pitch. That's going to be the path, that circular path that the pitch diameter is on. We talked about addendum, which is from the pitch diameter circle to the top of the tooth. Dedendum is from the pitch diameter circle to the bottom of the tooth. Clearance, we didn't talk about clearance yet. I'll show you clearance. We don't end up calculating it, but it's important to know that it's there. So when I look at two teeth that aren't engaged with one another, right here is clearance. From the top of one tooth to the bottom of the other, that gap that's created is going to be the clearance, okay? And that's the difference between the addendum and the dedendum. Pressure angle, okay? Pressure angle is important. So as we look here, I think we can get across right here. You're going to notice that when these come together at that point, they are going to create what we call a line of action, okay? And that's going to go through here. When we measure that line of action from the horizontal, the angle that's created between the horizontal and that line of action is called the pressure angle, okay? There are three pressure angles. There's a 20-degree pressure angle, there's 25, and there's 14.5. I'm not going to worry about that at the moment, but we'll talk about that a little bit later. So when we have teeth that are engagement, they not only have to have the same size tooth, the same diametral pitch, but they have to have the same pressure angle as well. Okay, pressure angle is important. Okay, so I think we hit all those. Involute tooth profile. So this is going to be the shape of the tooth on a spur gear. So specifically, we see it on figure 910. Okay. Figure 910. So it's at the bottom of page 265. This is our involute tooth profile. Now, if we wanted to draw it and we wanted to make it perfect and we wanted to, you know, create each and every one of the elements there, these are going to be the equations for the addendum, the dedendum, the working length, the circular tooth thickness, the fillet radius, all that kind of stuff. But luckily for us, CAD profiles in programs like SolidWorks and Creo and such, all we have to do is put in a couple parameters and it automatically creates it for us. So we won't worry about creating drawings to try to draw an involute tooth because technology will do it for us nowadays. Okay, but if you ever wanted to or needed to, they are standards based on the diametral pitch. So you'll notice that the diametral pitch here you need to know, and then you can figure out each one of those based on the equation. Okay. All right. So let's look at an example here. Let's do this one together. So we want to determine what is the pitch diameter. I'm sorry, what is the diameter of the pitch circle? Or yeah, the pitch diameter for the description of example problem 10.1. So underneath our camera here, we're going to look at the top of page 266. And what we've got is, says we have a 20-degree full depth involute spur gear. So it's our standard tooth size with the 35 teeth that has a diametral pitch of 10. Determine the pitch diameter of the pitch circle. And then it says the circular pitch and the base circle. The only one we're going to calculate here is just going to be the pitch diameter. Okay. So as we look at our first equation that we put on our equation sheet, that's going to be the equation that we're going to use for our problem. Need to find my pencil. Okay. So we know the relationship here is diametral pitch is equal to the number of teeth divided by the pitch diameter. So pitch diameter is small or lowercase d, number of teeth, and diametral pitch. Now in the problem that we have here, they want us to determine the diameter of the pitch circle or the pitch diameter. So example 10.1, we want to find out what is the pitch diameter. Okay. Now in the information that they're giving us the number of teeth. Okay. So we know n is equal to 35 teeth. And we also know that the diametral pitch is 10. So capital P sub D is equal to 10. So the equation that relates these three variables is this one right here. So our base equation is diametral pitch is equal to number of teeth divided by pitch diameter. So in this case, we just need to rearrange, use our algebra to solve for our lowercase d here. So to do that, basically multiply up, and then we're going to divide on both sides. So d is going to be equal to number of teeth divided by diametral pitch, right? That's our algebra. So now we can plug in our information. So we know that there are 35 teeth, okay, divided by our diametral pitch. Now, units for diametral pitch, as we said earlier on our equation sheet, we said that diametral pitch has units of teeth per inch, and it does, except nobody says them. Okay, they just said there's a couple ways that we know it's a diametral pitch. They'll say the gear is a number 10. Done. That's diametral pitch. It's a number 10 gear is the diametral pitch. Or they might say something like the diametral pitch is 10, but they'll never put the units in there. All right. So we have to put them in so that it comes out for us. So we know that our diametral pitch is 10, but its units are teeth per inch. Teeth per inch. So that means top to bottom, our teeth are going to cancel, and we end up having inches in the denominator of the denominator, which is a multiplication on top. So do you see how there's inches left over in this problem? Does that make sense to everybody? Yeah. Okay. So that means if we take 35 divided by 10, our pitch diameter here is going to be 3.5 inches. Okay. And that's it. Circular pitch and the other one, again, we're not going to calculate because those would be values that would come automatically. This pitch diameter is the most important thing for you, especially when you're going to be incorporating it into a design and you need to know what size you need to accommodate for. Okay. Questions on that at all? All right. Then let's go back and keep going. Standard gears. Okay, standard gears. So we already looked at that that table 10.3, and that table 10.3 has equations to determine the size of the gear profile of the teeth based on the diametral pitch. Okay, so once we know our diametral pitch, we can calculate anything we want about it. But like I said earlier, with technology, we really don't have to. And we can put a couple parameters into a parametric software, and those teeth can be created for us. Now let's look at relationships of teeth that are, or relationships of gears that are in a mesh. Center distance. Center distance is going to be that center to center distance between two mating gears, right? So the equation to solve for center distance is going to be found at the top of page 268, and it's going to be equations 7, 10.7, and 10.8. Okay, so this is our first equation, and then this is our second equation. So we're going to want to grab out our gear equation sheet, and we're going to add these two equations to it. So for center distance, C is going to be equal to, it's going to be R1 plus R2, which expanded out is going to be the pitch diameter of 1 divided by 2 plus the pitch diameter of 2 divided by 2. So this would be the first gear in mesh, and this would be the second gear in mesh. Okay, the pitch diameters of each. And then to calculate the pitch diameter, we have the relationship up here. Now, if we substitute the values for D with our number of teeth and our diametral pitch, we can then use the equation down here. So we can also say that center distance is equal to the number of teeth in 1 plus the number of teeth in 2, which is the pinion and the gear, divided by 2 times the diametral pitch. So N1 plus N2 divided by 2 times the diametral pitch. So it depends. If I happen to have 2 gears in front of me, and I don't necessarily have a tape measure with me, or I can't accurately find where is that pitch diameter because it's not an actual point on the gear, what I can do is I can count up the number of teeth around the outside of each one of those gears, knowing the diametral pitch, and I can still find a center distance. So depending on the information we have, if I have physical diameters or radiuses, or if I have just the number of teeth and the diametral pitch, I can find center distance in either one of these situations. Okay. So we've got another example. Let's do this one together too. So we want to determine a center distance between a pinion and a gear for the concrete mixer in figure 1010. Okay, in figure 1010. So as we look at figure 1010, we want to first determine what variables are we given, what do we need to calculate, what equations do we have that we have available, and what's kind of nice is we don't have a ton of them. We've got just a couple to pick from, and then kind of devise our plan for how we're going to approach this. So let's look at the complete kind of picture here and see what we've got. So first off, on this example, it says we have 2 5-pitch 20-degree full depth gears are used in a small construction site cement mixer. Now, you'll notice that it says 5-pitch, and this is where it can get confusing because we've got pitch diameter and we've got diametral pitch. Notice that they're not using any units with the number 5. So that means we're what? Do you think it's a diametral pitch or a pitch diameter? It's a diametral pitch because remember, that's the size of the tooth, and we don't call units of teeth per inch, all right? If it was a pitch diameter, it would have inches in back of that 5, okay? So diametral pitch. So we would say for this example, example 10.2, our diametral pitch is going to be 5. Okay, diametral pitch is going to be 5. Now the 20-degree full depth gear, that's going to be the 20-degree pressure angle. That's not going to come into any calculations, but it is important when we specify 2 gears that are in mesh. They have to have the same diametral pitch and they have to have the same pressure angle. Okay, so even if it has the same diametral pitch, but it has a different pressure angle, those still are not going to mesh correctly. Okay. So they're used in the cement mixer. Now the gears transmit power from a small engine to the mixing drum. This machine is shown down below. The pinion. Now, when we have 2 gears in mesh, the pinion will always be the smaller of the 2 gears. The gear will be the larger of the 2. So you have 2 gears in mesh. One is the pinion, one is the gear. Pinion is smaller, the gear is larger. So the pinion, the smaller gear, has 15 teeth. And the gear has 30 teeth. Okay, so you'll notice that I have N1 and N2. So whenever we have number of teeth, we know from our equations, number of teeth is N. Okay, now N1, a 1 is going to mean that that's going to be our pinion, and a 2 is going to be, that's going to be our gear. Okay, and then determine the center distance.
Is N1 always going to be smaller than N2?
Yeah. Yeah. Good question. Determine the center distance. So in this case, actually, we're going to write down more of what we know. So we also know we have an N1 is equal to 15 teeth. And I'm going to put in parentheses pinion until we kind of get used to that. And then N2 is going to be 30 teeth. And we'll put in parentheses, this is the gear, okay? Again, 2 gears that are a mesh, the smaller is going to be called the pinion, the larger is going to be called the gear. And then ones are going to be pinions, or what we're going to refer to a little bit later as the faster moving gear. It's going to be going around faster, and then the 2 is going to be the slower. We want to now determine what the center distance is. So we want to say center distance question mark, okay? So we go to our equation sheet and we see, oh, look at there. There are 2 equations for center distance. The first one needs pitch diameters, right? We don't have any pitch diameters. But the second one has number of teeth and diametral pitch. Ding, 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 right? That's the one we're going to want to use. So to find this center distance, I'm going to write our equation out in variable form first. N1 plus N2 divided by 2 times the diametral pitch. So our number of teeth on number 1 is 15 teeth, plus the number of teeth on 2 is 30 teeth, divided by 2 times the diametral pitch of 5. Well, and we want to put our teeth per inch in here, okay? So as we look here on the top, when we combine the 2, this is going to be 45 teeth, right? So I'll put this over here, 45 teeth divided by 2 times 5, which is 10 teeth per inch, right? Now you don't have to show all of these steps, but I want to show you kind of the units so that you can kind of see how this works. So the teeth are going to cancel again. I'm in inches in the denominator of the denominator. So it's a multiplication time up on the top by inches, and a center distance. We are expecting inches, right? That's a distance. So our C, is going to be 45 divided by 10, or 4.5 inches. Okay. Piece of cake. Now, in the example in the book, they went a step further and they calculated each individual pitch diameter using the n divided by diametral pitch equation, but you don't have to do that. All right, we've got these directly. They're kind of showing that you can get the same answer with both methods. All right. All right, questions there? This is fun, isn't it? I bet you can't wait to do your homework.
What was R?
R was just radius of the pitch diameters. Radius of the pitch diameter. Yep. Yeah. So notice that it expands out to pitch diameter divided by 2 and pitch diameter divided by 2. Mm-hmm. I guess I could put those on the side here, right? N1 is equal to radius, and that's going to be in inches. R2 is also radius in inches. And C is center distance.
So what's the difference
between R1 and R2?
R and center distance?
There isn't. It's just that this is the radius of one gear to the next. So when we look at, I think this is the best picture in here. So if I go from center distance, the center of one pinion, for instance, to the gear, it's the radius of the gear plus the radius of the pinion. It's just the physical distance. Or if I take the pitch diameter and pitch diameter, add them together and divide by 2. So center distance is the distance between the center of one gear in mesh to the next. Does that make sense? Yeah. Yep. Good question. All right. This is fun. So no CAD yet. What do you think? You gonna miss it? No. David said, nope, not gonna miss it. We'll just take a short break. All right. Gear kinematics, velocity ratio and pitch line speed. Velocity ratio, you've probably heard gears where they talk about a ratio. And velocity ratio is going to be the angular speed of the driver gear. Okay, we'll talk about that in just a bit. Divided by the angular speed of the driven gear. Okay, now these are going to be equations 17 and 19. So, oh, here we go. At the bottom of page 273, and we've looked at this diagram a couple times here. All right. when we look at velocity ratio, capital V, capital R, velocity ratio is going to be equal to the angular speed, W, of the driver. So driver is where the motion is coming in, all right? And most often that's coming off of our motor, our engine, whatever it might be. It's the higher speed of the two rotating, all right? And then we want to divide that by the angular speed, the W of the driven gear. So where we're going from the input to the output, if you would, all right? So when we look at this pair of gears here, the pinion, the smaller one, is going to be, for instance, mounted on our motor. That's going to be our driver. Our input is coming in. This is going to be the faster moving gear. It's going to engage with this much larger gear, which is then going to rotate in the opposite direction, but it's going to slow down, okay? And it's going to slow down because as we look at around the outside here, this is going to have more teeth. This has fewer teeth. So my pinion is going to need to go around more times to get this one just to go around once. Do you see that? You guys see that? So this velocity ratio is looking at what is the angular velocity ratio of our input, our driver, to our output, our driven, the one that's going slower. So how many times greater does that driver have to go around to get the driven one to go around once? Okay. Now that number sometimes is going to be an integer number. So it might be 2 times, it might be 4 times. And what that means is that the gear, if it's 2 to 1, for instance, that means that this has to go around 2 times before this is going to go around once. So if I have 20 teeth, I used my wrong number. If I have 20 teeth on my pinion, then if I'm a 2 to 1 ratio, my gear has to have 40 teeth. If I'm a 3 to 1 ratio, if my pinion has 20, then this has to have 60. But I don't have to be an integer number. I don't have to be an even number. It might be 2.86754. It doesn't matter. All right. That just means that the pinion has to go around that many more times, however, whatever that number is, to 1 time on our gear. Okay. 1 time on our gear. Right. So we call that angular velocity of 1, which is going to be our input or our driver, divided by the angular velocity of our driven, or our gear in this case, number 2. Okay. Now, as we just illustrated, we can do this not only with the angular velocities, but we can do this with the number of teeth. And if we know the diametral pitch and the number of teeth, we can do it on the pitch diameters as well. So as we turn the page, up at the top of page 274, here are all our options for calculating velocity ratio. Okay, so we're going to add this equation, these options, to our equation sheet. Okay, so we're going to say velocity ratio is equal to W1 divided by W2. Okay, so W1 is going to be angular velocity. So it's what we've been using here, but this is going to be of the pinion. Okay, it's going to be of the faster moving, the smaller gears. W2 is going to be the angular velocity, but this time of the gear, the larger of the two that are engaged. Now, that's one way I can calculate the velocity ratio. Oh, and I should say as well, this is going to have units of RPM. And the reason we can leave it in RPMs and don't have to go to radians per second is because it's a ratio. So the units are going to cancel out. So whether I have radians per second or if I have RPMs, it doesn't matter. We're just looking at the ratio between the two numbers. Okay. Now the next way that I can calculate velocity ratio is to take the radiuses, radius 2 divided by radius 1. Now, you'll notice something about this velocity ratio. My larger number always has to be on top. So between these two, my faster angular velocity has to be on top, which is going to be number 1, the pinion, divided by number 2, the gear, because the gear is going to be going slower. But now when I look at physical size, the radius of the gear has to go on top, divided by the radius of the pinion underneath. Okay, so R1, radius 1 is going to be pinion, and R2 is going to be gear. Okay. I can also do it for pitch diameters. So D2 over D1. Okay, D2 is going to be of the gear, and D1 is going to be pinion. Okay. And I can also do it for number of teeth. So N2 on top and N1 on the bottom. So this is going to be gear. This is going to be pinion, because I'm going to have more teeth on my gear than on my pinion. It's just it's the angular velocities that we have to watch out. The pinion has to be on top and the gear will be on the bottom, because it's the faster moving one has to be on the top. The larger number has to be on top. Okay, any questions about that? Okay. Then I believe we're moving into an example.
Sorry, what is the ratio?
Nothing.
Oh.
Nothing, because each time you're going to cancel out. So if this is RPM, there's nothing. Oh, and I should put, right, velocity ratio. And it's just that, it's just a number, and it's not going to have any units. And anytime that so I can't, for instance, I can't have angular velocity and then put a number of teeth underneath, because then I won't get my cancellation. They have to be the same units top to bottom. Okay. And we'll use these in some examples. You'll get used to it. Okay. Okay. So let's look underneath here. Let's look at example 10. So in this one, we want to determine the speed of the mating gears in RPMs and calculate the pitch line speed. Oh, I didn't talk about pitch line speed. We got to go back. Sorry. It is here. Pitch line speed. So yeah, we're not quite ready for the example. Let's talk about pitch line speed. Pitch line speed. Okay. So we're going to go back to the illustration on 273. Okay. And what we're going to do is we're going to look at our gear here. Okay. And I'm going to draw this back in. So at the center of our gear cannot move, right? So we can simulate that like that's a frame member, right? Okay. And the center of rotation, if we show, like, for instance, a radius, like kind of like representing a link, and I go right to that point of engagement, do you notice how that looks like just like a regular link that we've had in our 4-bar mechanisms, for instance? Okay. Now, at that point of contact right there, that's going to be where we have engagement with the other pinion. And if we look here, if this is rotating around a W2, an angular velocity, we know that if this link, this gear, is rotating and has a fixed center, it is going to have a straight line velocity component that is perpendicular to the radius of rotation in the direction of rotation. So do you see how pitch line speed is our straight line velocity component that we've been looking at in our 4-bar mechanisms? So good. Nothing new here. Isn't this fun? Jesse's having a lot of fun. Just kidding. All right, so pitch line speed. We know how to calculate this. Watch this. Watch this. You're gonna tell me what I'm gonna write. VP, pitch line speed, is equal to, what is the equation for straight line velocity component of a link rotating around a fixed center? There's a W.
Yes. R.
And an R. Yes. And look, when we turn the page, they just put the R first. There's the equation. Look at that. Now they call it, I shouldn't call it pitch line speed. They call it tangential speed. Okay. And that makes sense because it's around the outside of the circle tangent to. Okay. So tangential speed or pitch line velocity is going to be equal to whatever the rotational speed is of that gear times its radius back to its center of rotation. So for instance, if this is a W1, this has to be an R of that same gear. If it's a W2, it has to be the R of that same gear, an R2. Okay, now, tell me the units of our radius. Our units are going to be what? Inches, right? But what are our units of W2? Not RPMs, they're the other ones. Radians per second, right? The same rules apply here again, right? Radians per second, because our pitch line velocity, what are the units going to have to be here? Inches per second, right? And when I take inches times radians per second, the radians do what? How do they disappear? No, they don't just disappear. They're like what? Aren't they like Lucky Charms? They magically disappear. Oh, somebody knew it. Yes, they magically disappear, Brandon. Thank you. Thank you. They're like Lucky Charms. So the radians magically disappear. They don't just disappear. They don't just go away. They magically go away. So, anyway, see, it's a good way to remember it, right? That's okay. Now, pitch line speed. Any questions about that? All right. So reapplication of something that we already know. So now we are ready to look at our next application. Okay. So example 10.8. Example 10.8. So we're going to do this one together again. We want to determine the speed of the mating gears in RPMs and calculate the pitch line velocity. So let's look. We want to figure out what variables we know, what we need to calculate, what equations. This is going to be fun. All right, there it is. There's our grocery checkout conveyor. Okay. So we have a set of gears that are down here at the bottom that are used to reduce the speed of an electric motor to a shaft driving a grocery checkout conveyor. Okay. The gear on the motor shaft is a 10 pitch. So again, notice that there are no units associated with this number. This is going to be our diametral pitch of the set of gears. So both gears have to have the same diametral pitch to mesh. And that pinion, the smaller of the two, has 15 teeth. So you're going to notice down here, they have 15 teeth. N1 is our pinion, 15 teeth. And it drives at 1800 RPM clockwise. So they're showing us the direction and they're identifying our W1 at 1800 RPMs. They want us to determine the speed of the mating gear. So the mating gear is right here. We want to know what W2 is. That's going to be what we want to find. And it has 45 teeth. So N2 has 45 teeth. So we need to determine the W2, and then we also want to calculate the pitch line speed VT. All right. So let's do example 10.8. What we know, what's given. Okay. PD is equal to 10. And I like to write the units because that way I won't forget about it. It's teeth per inch, even though they don't give it to us. That's what they are. We know that N1, which is the pinion, is 15 teeth, right? I'll put a pinion in. And pinion, remember, is our smaller of our two engagement. W1, is that what they're calling it, right? Yeah, W1. So the angular velocity of the pinion is going to be 1800 RPMs. And we need to find, okay, we need to find W2, okay. Oh, we also know, oh, I don't have room, so I'm going to say N2 is equal to 45 teeth. That's given after the fact. And then we also need to calculate our pitch line speed or our tangential straight line velocity component. So we have our equation sheet. As we look here, we know what our input speed is, and we know the number of teeth, right, on each one of those gears. So what we can do is we can take this velocity ratio and we could pull out the W1 over W2, and we can set it equal to the number of teeth 2 over number of teeth 1. So let's do that. So step number 1. So we want to find W2, right? So we can say W1 divided by W2 is equal to N2 divided by N1. Okay. We know W1 is 1800 RPMs. We know the number of teeth on the gear is 45. And we know the number of teeth on the pinion is 15. So our only unknown is the W2. So we just need to rearrange this algebraically and solve for W2. So go ahead and do that. Go ahead and do that. So to solve for W2, we've got to get it on top, right? So we need to multiply it up on this side, which means we got to get N2 is going to come on the bottom to get W2 by itself. And then N1 has to multiply up on top. So that's my rearrangement there. Make sense? So now we can just put our numbers in. So we know W1, or our angular velocity of our pinion, is 1800 RPMs. Multiplied by the number of teeth on the pinion, which is 15 teeth, divided by the number of teeth on our gear, which is 45 teeth. Okay. Teeth cancel out top to bottom, so we're left with RPM, which is what we're expecting for a W2, so that's good. So now W2, take 1800 times 15 divided by 45. Did I do that right? 600. And my units are RPMs, right? That's what's left over. That's what didn't get crossed out, RPMs. Now, to complete this and to fully define it, we should identify its direction of rotation. So as we look here, since W1 is going clockwise, W2 has to go in the opposite direction, right? Counterclockwise. So we do want to add that to the end here, counterclockwise, as part of the answer. Okay. So that's our first one. We got W2 done. The next one is going to be the pitch line velocity. Okay, so part 2 is going to be pitch line velocity. We go back to, what the heck? I hate pop-ups. I don't understand. And I try to turn them off and I don't know. They don't seem to completely ever disappear. So here's our equation for straight line velocity, right? That pitch line speed. So we are going to take what we know. Well, we do know the W2 now, but it is a calculated value. So we'll use the W1 and the radius 1. Okay. So we're going to say VT is going to be equal to W1 times radius 1. We can expand that out and we can say, oh, we can take W1 times maybe the diameter 1 divided by 2. But if we look on top here, do we have a diameter? Can we calculate a diameter? We can. We go up to the top of our equation sheet. We know the diametral pitch and we know the number of teeth, right? So we are going to calculate the pitch diameter of the pinion. So D1 is going to be equal to the number of teeth on number 1 divided by the diametral pitch. Okay. So we know that number 1 has 15 teeth. And we know that the diametral pitch is 10 teeth per inch, right? Teeth cancel out, we're left with inches. D1 is going to be equal to 1.5 inches. So that's the number we're going to put up there. Okay, so we've got that one done. But what about W1? We know that it's 1800 RPMs, but we know in this equation, we can't use RPMs, can we? We have to change it to radians per second. So we need to convert our W1, which is 1800 revolutions per minute. And we need to convert that into radians per second. Did you get 88.5 or 188.5? Yeah. Okay, great. So now this is what we're going to put up there. Okay. So VT is equal to 188.5 radians per second times 1.5 inches divided by 2, right? Because this is the diameter and we need the radius. So we have to divide by 2. So our straight line velocity, I get 141.37 inches per second. No, this is a belt or a conveyor. So the most common units to use for a belt or a conveyor speed is feet per minute. So you'll notice that they have feet per minute in their answer. So let's just confirm that we get their numbers. So 141.37 inches per second. And we're going to convert that to feet per minute. So that means I have 12 inches in 1 foot. So my inches cancel top to bottom, and there are 60 seconds in 1 minute. So cancel top to bottom. So 141.37, 60 times 12 divide. So our VT is 706.85 feet per minute. And you can write FPM, and that's what they have. Yep, 706.9 feet per minute. Cool. Any questions? All right, let's see where we're at on our PowerPoint. All right, spur gear selection. Spur gear selection is going to be our next section here. So the designer only needs to specify the following parameters to completely identify a gear, a standard gear. You need to know the diametral pitch, which we've talked about, P sub D. We need to know the number of teeth that we need on that gear. So what is our N? And we also need to specify the pressure angle. Okay. So we talked about the pressure angle a little bit already, but we'll talk about it a little bit more here. But diametral pitch first. Diametral pitch is always going to be the first parameter that's going to be selected for a set of gears. Now that diametral pitch is going to be the size of the tooth as we had seen earlier. So the larger the number, the smaller the tooth. Okay. Any questions about diametral pitch and how it's different than pitch diameter? I think we've emphasized that quite a bit at this point, right? With the examples we've done. Okay. So remember that gears that are in mesh have to have the same diametral pitch, same size tooth. Now, as we look at table 10.6 on page 275, this serves as a guide for a place to start for diametral pitch. So if you're wondering, like, what size tooth do I need? Okay, there are going to be tables that you can look to for guidance and for a starting point. So table 10.6 here uses the pinion RPM. You're usually, worst case scenario is always your faster rotating gear, which is going to be your pinion. And then you want to know how much horsepower am I pushing through there? So you want to line up your pinion speed about to however much horsepower you have. So if I have 1800 and I have 1 horsepower, I bring those together. That means that I'm going to start with a diametral pitch, a suitable diametral pitch for 20-degree mild steel gear. So this is a mild steel gear material on my gear. I'm going to start with a diametral pitch of 20. Okay. And if we look back on page 263, you know, as we look comparing to other common sizes, it's considered a pretty small tooth. All right. In the scheme of things, most industrial applications, we're going to be sitting 8s, 10s, and 12s right around here. Okay. Kind of that midpoint. So this is a little bit smaller size tooth. Okay. But what this chart does for us is rather than like just guessing or pulling a number out of the air, it gives us a place to start. See, there's a question here. Are those full scale? When we say full scale. Oh, the pictures. That's a great question. I wouldn't say yes. I would not say yes, but I don't think they're terribly off. And I think what it does is it gives us kind of a good comparison between. I will track down some gears and see if I can find some that are a better representation. Yeah. Comparatively, yes, I don't think they're terribly far off, but I don't think we can say definitively I could measure that and know that that was to scale. Okay.
I mean, technically that would be per inch, right? We could count how many feet,
Well, it's not exactly that. It's per inch of pitch diameter. So it's looking at, so when we look at this right here, if we look at a gear, it's looking at how many teeth can I fit across the diameter. So this is like along that pitch circle. Does that make sense? That's what it's actually doing. So yeah, they might be close, but I wouldn't measure them because it's in a textbook. Okay. All right, let's go back over here.
So are we gonna need to like bookmark it and refer to table 10.6?
For, yeah, some examples and also some homework that you're going to do. Yes.
Okay.
So again, this is a place to start, and this is for mild steel. So if you had different types of materials, then you would look to a different chart. Okay. This is also going to be a 20-degree pressure angle. So let's talk more about pressure angle on our next slide here. There are 3 standard pressure angles. The most common and where we always start is going to be on a 20-degree pressure angle. This is general industrial applications. When we start looking at high speed and low power applications, we're going to look to 25-degree pressure angles. So the pressure angle gets a little steeper. And then 14.5, those are only for replacement parts, meaning they used to be one of the standard 3, but what's happened is they've now standardized on the 2. And so you can get 14.5, but you don't want to design it into any new equipment or new designs. Okay. It's only for replacement parts. Now, gears that are in mesh have to have the same pressure angle. Okay. So if we go back to the diagram on page 264. Okay. As we have that point of engagement and we see one of these teeth come in on the other, and there's what we call a base circle. That base circle line is going to be tangent to one. It's going to go through the point of engagement, the pitch diameter, and then it's going to be tangent to the other. This line with the horizontal makes what we call the pressure angle. Okay, it's where the resultant, and although in kinematics here, we're not worrying about forces, but we are transmitting forces here. There's 2 forces. There is a radial force and there is a tangential force. So when this comes in, for instance, and it represents the tangential force, it's going to be the horizontal component. This is going to be the radial, which is going to be the vertical component. And guess what? The resultant is along our pressure angle. Okay. So although we're not dealing with forces right now, pressure angle is important. And we'll talk more about it in design of machine elements, but know that that's going to be where that resultant force is going to be. That's going to have the components that are tangential and radial coming in at that point of engagement. Now, why the 3? So 20 degrees is our standard. So let's say we have a component. If we draw this across, this is going to be our component in the Y direction, right? And this is going to be our component in the X direction. If this is 20 degrees, that's what our number is, or that's what our lengths of our magnitudes look like, right? But now let's increase that. Let's put that to 25 degrees. Same force, 25 degrees. Notice how you're going to get a taller radial and a shorter tangential as it crosses here. Do you see that? Now, the advantage of this is when we have, for instance, high forces, high torque that we're pushing through here, high horsepowers, where we need bigger, chunkier teeth. So when we get to the larger teeth, we're expecting that we're going to be like really kind of, putting those teeth, through some heavy duty forces and heavy duty transmitting of torque. Then we're going to go to a 25-degree pressure angle because, as you can see here, if we look at just one tooth and we're pushing over that tooth, it's kind of like a cantilever beam or kind of like a diving board. It's only supported down here. So if this force gets too great, what's going to happen to that tooth? It's going to shear off, right? So when you have a 20-degree pressure angle, you have a larger tangential force. When you have a 25-degree, you have a shorter or a smaller tangential force. And that's why when you have bigger, chunkier teeth, bigger forces that you're pushing through, you want to direct that down towards the center of rotation where you've got more material to direct that to. Okay. Now, 14.5. This also tells us why when we're more shallow, what happens? For that same force, the tangential is going to get even taller. The radial is going to be smaller. So why do you think we don't do 14.5s anymore? Because they're going to shear off teeth more easily, right? You're going to have more, breakages. So only for replacement parts. Don't ever design 14.5s as new designs for gears. Okay, 20s is where you start, 25s if necessary. But those are the 2 standards for new designs. Okay, pressure angle. Any questions?
Why wouldn't you just do everything?
Sometimes like they're getting a lot of moves, high speed.
That's exactly it. Yeah, thank you, Jesse. Yeah, so what you can have is they're going to be the bigger, chunkier teeth that are going to have the higher pressure angle. They're going to need more force to move them around. Yeah. And what?
Like high torque.
Exactly. Yeah. And so 20s are always, it's usually like your first round, that you're going to go with. So when we're in machine design later on, we're going to take this, we're going to start adding in these forces and figuring those out. And then we're going to be looking at the stresses that are generated. And then we're going to be picking, what is the appropriate size based on the, a little bit more of the details of the application rather than just rotational speed and just space where torque is or where kinematics is. But good question. Anything else? All right. So that's pressure angle. So that's all we really need to know about pressure angle. We just need to know that we need to specify the same pressure angle when we have 2 gears in mesh. Number of teeth is the last one. So when we look at number of teeth, this is going to influence your velocity ratio. If the pinion and the gear have the same number of teeth, then they're going to be rotating at the same RPMs. But as we said earlier, the most common application for gears is where we're going to want to slow down and the speed and then increase the torque. So we're going to have different size pinions to gears. The number of teeth must be an integer. Why is that? Why does the number of teeth have to be an integer? I can't like put on a gear like a half a tooth, right? Or a 0.2 of a tooth. So yeah, we have to have an even number of teeth on any gear. And then, but you have to be careful. Manufacturers are not going to stock each and every integer. So you have to know based on your diametral pitch, what are the available number of teeth that I can get on a gear? And if we look at table 10.7, these are going to be the common numbers of teeth for common pitch diameters or diametral pitches, sorry. So on the bottom of page 276 is where this chart starts and it continues to the next page. So this is number of teeth commercially available in stock gears. So for a diametral pitch of 30, so one of the smaller ones, notice that we have number of teeth are going to be 12, 14, 16, 18, 20, and so on. Okay. Notice it's not every number. Okay. You're going to then go over, and these are going to vary between sizes. You're going to go over to a diametral pitch of 10, for instance. And now we've got 12, 14, 15, 16, 18, 10, 20, and so on. So not all the numbers are there, and it could even vary by manufacturer, depending on who you buy your gear from. Okay. So you want to always have like a catalog open or a list like this open. And these are going to be the ones that are common for the diametral pitches that are most used. So let's look at example 10.9, example 10.9. And we'll go over, I'm just going to peek here. We're going to do 10.10 and then coming next. Okay, so 2 more examples. Just kind of looking at our time. I think we're just going to get through this first part tonight. We won't have enough time to finish up, but that's okay. We'll do that when we come back from our break. So as we look at example problem 10.10, we have a gear reducer is used for a concept of a small trolling motor for fishing boats. The gears must transmit 5 horsepower from an electric motor at 900 RPM to propel at 320 RPM. So this is the difference in from our motor to the trolling, or to the blades of that. Would you say trolling motor? Is that right? To the output?
Yeah.
Then we want to select a set of gears that is going to accomplish this task. Okay. So we're kind of starting with nothing, right? They're only giving us the reduction of the speed and how much horsepower that we have to deal with. So what we want to do is the first thing when we're specifying gears is we need to determine what is the size of the tooth that we need to work with. So we are going to go back to table 10.6, and assuming mild steel gears, we want to find the RPM of the pinion, the faster one, and that was 900 RPMs, okay? And we know that we're pushing 5 horsepower through here. So we're going to go 900 down to 5, and notice that the number is a diametral pitch of 10, okay? Diametral pitch of 10. So for our step number 1 here, let's say example 10.9. Number 1, our diametral pitch is going to be 10, and we can write teeth per inch. Okay. And this is from table is that table 10.6. Now, if you are dealing with, or are you specifying from a specific vendor, you will have their catalog open and looking at what they have available in this size. Okay. Then what we're going to do is we need to find, I didn't go through my process here. Oh, wait. That's okay. We're going to do 10.10. We'll skip 10.9. Sorry. We already went to 10.10. This is our last example, actually. I skimmed over that one. So now that we have our diametral pitch, the next thing that we need to do is we need to use the required velocity ratio to determine what our number of teeth should be on our pinion and our gear. Okay. So we know that our velocity ratio can be accomplished or calculated in a couple different ways. The rotational speed of the pinion over the rotational speed of the gear, and we want to find number of teeth. Okay. So what we want to do is we are going to take that velocity ratio. We're going to say velocity ratio is equal to W1 divided by W2. Now, W1 is on the pinion, the faster moving one, and we know that to be 900 RPMs, right? Divided by the slower moving, which is 320 RPMs. So this cancels out, and our velocity ratio is going to come out to 2.8125. Okay. Unitless because the RPMs cancel out. Now, we also know that our velocity ratio equals the number of teeth on our gear divided by the number of teeth on our pinion. So we can say velocity ratio is equal to N2 divided by N1. Okay. Now, we know what the velocity ratio is, all right? But we want to now figure out what is, the appropriate numbers that we can use here. So we're going to rearrange this. So we're going to say N2 is going to be equal to the velocity ratio times N1, okay? Or N2 is going to be equal to 2.8125 times N1. All right. So we still have two unknowns, but our pinion is the smaller of the two. So what we want to do is we just want to kind of try some things here. Now, it said that we had to accomplish 320, right? So if our motor is running at, or our engine is running at 900, we have to get that trolling motor down to 320, or the blades, right? So what we're going to do is we are going to use this velocity ratio, and we're going to see if we can find any combinations in the diametral pitch of 10 section that can accomplish this exactly. Okay, so we are going to start with looking up here in the diametral pitch of 10 section, and we're just going to start with the number of teeth on our pinion to be 12. Okay, so if we take N2 is going to be equal to 2.8125 times 12, what do we get for our N2? Right. So we get 33.75. Obviously, with the 0.75, that means that we can't use 12 as one of them. So what are we going to do next? Keep going. Yeah, let's try 14. So we can say N2 is equal to 2.8125 times 14. And we get N2 is equal to 39.375. Not going to work, right? So then we go to the next one. This fun. Let's try 15. N2 is equal to 2.8125 times 15. $42.1875. Not going to work. Next one. One of these has to work, right? $45. I got an even number. Now I got to look. Hopefully, I'm going to cross my fingers. Is 45 one of my options for a diametral pitch of 10? Oh, thank goodness. Oopsie. Thank goodness. So that's an option for me. Okay. So I could say that the number of teeth on my pinion, N1, is going to be equal to 16, and N2 is going to be equal to 45. And this is teeth and teeth.
No, it's 16. You said 6. You said 16. But you said...
Oh, I wrote 12. See, you know how your mom would say to you one thing, but you knew what she meant? It was something else.
Mhm.
Yeah, I get to use that. I know. Isn't that funny? Okay. So we picked our number of teeth then. All right, let me see. What else do we have to calculate here? Center distance and the pitch diameter. Okay. So now we're going to figure out our center distance now that we know our gears and we know our diametral pitch, right? So number 3 is going to be our center distance is equal to. Now we have two equations. We can either use pitch diameters or we can use number of teeth and diametral pitch. We know our number of teeth, right? We just picked it out, and we know what our diametral pitch is. It's 10. So let's use this equation because that's what we have. So we can say N1 plus N2 divided by 2 times diametral pitch. So this is N1, we said was 16, right? Plus 45 teeth divided by 2 times 10. And I should write my units in there, sorry. teeth per inch, right? Teeth cancel top to bottom. What's my number? You get 40.5. That's all right.
Yeah,
30.0. Let me try. I did it fast. 45 plus 20 divide. Yep, 3.05. And that's going to be inches. Okay, center distance. And then we need pitch diameters of each, right? So pitch diameters of each is going to be a D. We're going to use this equation up here. We know the number of teeth of each and we know their corresponding diametral pitch. So D1 is going to be equal to number of teeth on one divided by the diametral pitch. So we know that the number of teeth on the pinion is going to be 16 teeth divided by a diametral pitch of 10 teeth per inch. So our D1 is going to be 1.6 inches. Okay. And then diametral pitch 2 is going to be N2 divided by the diametral pitch. Said that wrong. It's pitch diameter. Number of teeth is going to be 45 teeth divided by a diametral pitch of 10 teeth per inch, right? So D2 is going to be 4.5 inches. And now one more check. If we add these two together and divide by 2, it should come out to be 3.05. Does it? Do you think? 1.6 plus 4.5 divided by 2. Sure enough. You don't have to do that check, but it's a nice one.
I mean, yeah, I just did the pitch diameter first and then.
Oh, did you?
Yeah.
There you go. Yeah, either way. So there you have it. There you have it. We skipped over number 9. Number 9 was a short little problem. I don't want you to feel cheated. So let's just take a peek at it so you know what it is. This one is just a pair of mild steel gears you want to select or are selected for that cement mixer. You want to determine the appropriate diametral pitch. So using the parameters here, you would just read the chart to find a diametral pitch. So we have 10 horsepower and we have 1800 RPMs. So we're going to go to that other chart. We're going to find 1800 and we're going to find 10 down here. So a diametral pitch of 10 would be where we would start with those sets of gears. But that's all that problem was asking, was just to read this chart to determine a diametral pitch. So at 8:42 today, I feel like we've gone through enough material, right? So, so when we get back from our Thanksgiving break, we will be ready to look at the second part of chapter 10. So I am going to take a peek here before we go, because I mean, even though it's Thanksgiving, you might be like, I'd really like to work on some of this kinematics because I really love it. I can't wait. So as we look at these oopsie, not the session recordings, I want to look at the assignment. Assignment number 5. The problems that you would be ready to do, and these are the end of chapter. I'm just gonna peek here. I just want to be sure. I have 5, 6. I just want to mark them. So we do 9, 13, 14, 15, 16, 25, 26. Okay. So as we look here, all the problems that are listed here besides the very last 2, you can do. Okay. So if you wanted to get started on these, you certainly may. Let's take a glance at what each one of them is briefly. I know you're ready to get out of here. So for number 5, it says we have 2 12 pitch, 20-degree full depth involute teeth. So our standard spur gears that we're given, the pinion has 18 teeth and the gear has 42. And you just want to do part A, which is figure out the center distance using that data. Okay. The next one is doing the very same thing using the data down here, just a center distance for number 6. Each one of these is just 5 points because it's just one thing that you have to calculate. Then we're going to go up to number 9. This one, we want to do both parts here. You want to find the pitch diameter and the center distance, but On number 9, it references internal teeth. Use the externals like we did, okay? Like the standard types of teeth. Don't use the internals here. So external teeth only. And then for number 13 and 14, same thing. Don't do the internals, do external teeth and do the pitch diameters and the center distance. Then for number 15, you're going to do the speed of the gear, which would be W, like W2, and the pitch line speed or VT. They're giving you an 8-pitch, 18-tooth pinion, rotates clockwise, 1150 RPM, mates with a 64-tooth gear. So what is W2 of that gear? And then the same thing, different numbers for number 16. And then the last couple problems that you have to do as we turn the page, numbers 25 and number 26. This is doing catalog gear selection. These are just like that very last problem that we did. They're giving you a description and you want to determine what is the set of gears that would accomplish that. Okay, so you want to determine the diametral pitch, the number of teeth that would be available, getting the exact speed reduction that you have here. Okay, so same process as that very last example that we just did. All right, so that's all I've got for you tonight. You are free to go. Does anybody have any quick questions before I let you go? All right, I'm going to stop recording.